So today we'll try to understand the cross entropy laws. So the cross entropy laws is a commonly used function in machine learning, and it's particularly used for classification tasks. Uh, it measures the difference between two probability distributions, that is the true labels or the actual class labels, and the predicted probabilities by the model. So let us try to understand this via a problem, a classification problem, a multi-class classification problem here. So, which is to classify a given image, which is basically a collection of pixelated values, into a table, a cat, or a chair. So we need to find a probability whether a given image belongs to one of the three classes, right? So the actual labels or the actual values for a positive class will be defined as below. So for a positive class, for a table, that is that means the given image is actually the image of a table. So the encoding, in one hot encoding, the value of this true label y would be 1, 0 and 0. That is, if the given image actually is the table, actually the image of a table, then in one hot encoding the y vector would be given as 1 comma 0 comma 0, and as so on and so forth. If it's a cat, then it will be 0 comma 1 comma 0, and for a chair it will be 0 comma 0 comma 1. That is 1 for those particular classes and 0 for the false classes, right? So this is how we define the real values. And now suppose uh, we have to put the cross entropy laws for this problem for a given single example for n classes. So here we have 3 classes, right? So n equals 3. So for the loss function in that case would be defined as negative of I equals 1 to n, that is the number of classes. Here the class number of classes is 3, and yi log of pi. So what is yi? Yi are these values. So yi is true label for class I, that is 0 or 1 in one hot encoding, which I already depicted over here, how one hot encoding works. And pi is my predicted probability for the ith class, right? So this is what the cross entropy loss looks like. So how this works is the true label yi is a vector representing the actual class of the sample, right? Like whether it is a chair or a cat or a table. So if the class k is correct class for a given example, then the vector y is one hot encoded, meaning all examples except yk are 0, right? Like if it is an image of a cat, then the y vector would look like, so cat was the second element, right? 0 comma 1 comma 0, right? And predicted probabilities represent the predicted probability that a sample belongs to class I, right? So it is often derived from a softmax output in a neural network. So pi for one particular class would look like, so you an image was given and you have a model which predicts the probability of of the image being a table, a cat, or a chair. So the maybe the probability for it being a chair is a table is 0.1, a cat is 0.7, and chair is the third one is chair, right? And for the chair is 0.2. So these are the real value of the vector and these are the predicted values for a particular example. So again, what will the cross entropy loss will look like in for this particular example? L equals negative of 0 times log of 0.1 plus 1 times log of 0.7 plus 0 times log of 0.2, which equals negative of log 0.7, right? uh, so so we can see if the repercussion of this particular formula is the model predicted probabilities, if they're closer to this particular value, right, then the loss would be much smaller. The main advantage of using a cross entropy loss rather than a mean squared error loss, root mean square error loss, uh, would be that cross entropy penalizes confident but incorrect predictions more heavily than the confident ones. Like if it is 0 and this value becomes exactly 1, then the loss would become much bigger, right? And if they are much closer to the value, that if it is much closer to 0 to the real values, then the loss becomes very small, right? um, and other than that, it provides a smooth gradient that helps to optimize the model parameters effectively using the gradient based methods. So that was all about the cross entropy loss.